Thanks for the introduction. It's my great pleasure to be here as a representative of our collaboration to give this talk, which I will talk about our recent paper released 1 month ago with my excellent collaborators, Sergio Cagulu, Dimitri Chicherin, Johannes Han, and Yang Zheng. Okay. Let me begin with some motivation of our work, which is rooted in the Parton scattering amplitudes in the QC theory. So basically, you know that recent year, due to the systematic development of the canonical differential equation method, as well as our improvement for the integration by part algorithm. So basically, you can in principle, we have some systematic way to say calculate the scalar amplitude in certain physical theory for certain particles at a certain loop order. So yesterday, I think Matthias and Bayu both gave a very excellent discussion for more detail about this. Basically, you begin with some integrand. So this integrand may calculate it from Feynman rules or some unitarity method. Something looks very physical. And to perform the loop integration, what you really do is so-called integration by part reduction onto a set of mass integrals. So it really looks like some scalar integrals. They are serve as linear basis for the integrated level result. And they can be calculated fully and systematically by the canonical differential equation method. So after this, so basically we can express your amplitude as a linear combination of your mass integrals with some prefactors. But most cases, this IP reduction is very huge, as Bayu yesterday talked about. So practically speaking, people will do it firstly by some numerical method. So first time you get is a coefficient will be at a very specific kinematic point, maybe a lot of, but it is a numerical result. So there's one more step, which is called the reconstruction for all the prefactors from their numerical result to an analytical result. After this, you can imagine that your amplitude has been expressed by some number prefactors times the kinematics prefactor times the mass integrals, which are known from the CDEs. So it's a generate divergence, so you subtract the divergence by some scheme, and finally you get a finite hard function. Okay. So it's a very systematic way, and based on this procedure, and also the massless Panda functions, the massless, I mean, external particles are massless, and also with a massless exchange, which is calculated up to 2 loop levels. So recently, we already have the 5-point Parton scalar amplitude in the QC theory up to next to next leading order. Since my title has a hexagon, so today, of course, I will talk about 6-point observables and the calculation. And we know that also a lot of Gangshu just now have talked about that recently. It's really a milestone in our area that we have the planar sector, all the 2-loop 6-point mass integral have been calculated from the canonical differential equation. So these are the excellent researchers that involved in this work. And I will please refer to Yang's poster upstairs. I think it's full of pink color and really full of love. So yeah, so please refer to him. We're very happy to fill in more detail about this study. So we expect that in the future, of course, we want to move on to the 6-point observables calculation. But of course, this moving on is not easy. You will face a lot of difficulties. To summarize, 2 of the main bottlenecks you should think of and have some modification before really calculate something. The first point is, as I said, in most cases, the integrand for any scalar element you care about is a really very big rational function, the monster. So when you do the IP reduction, first you can only do it in most cases in a numerical way. And secondly, even this is still very computational intensive and time consuming. Second point maybe is more technical and more tricky is mostly after you get this numerical result for the IPP, you have to recover the prefactor from the numerical result. This step is also not that easy because the reason that by now we still have very little understanding about what kind of kinematics prefactor QC amplitude should have. So this will be my 2 main concerns of today's talk. I will look first into some toy model that define the formal theory, which share similarity with the QC amplitude, and to see if we can get some advanced understanding or say some modification in this calculation. Okay, so one more slide for this hexagon functions because it's super important in today my talk. So this is a very typical canonical differential equation project. So what you need to do is straightforwardly, you look into these 6 very, very non-trivial Feynman integral sectors, construct what we call the UT mass integral basis, and finally set up the canonical differential equation system between them. And yeah, so by which you can just calculate all the mass integral systematically. And yeah, at least just the information I need in my talk. Its conclusion from this paper is, if you need all the function to express the two-loop finite observables, in total you need 945 independent linear bases. In other words, for every observables with this 6-particle input, finally by Amplitude reduction you will reduce your target onto this 945 functions. Okay, so it's a much bigger basis than the 5 points, and we're seeking some modification. Some of you may be very expert in the hardcore calculation for scatter amplitude. So you see that you may see that, okay, if I cannot calculate something from the integrand, then I will do a bootstrap calculation from the integrated level. Okay, this is also one point that raised by Anastasia this morning, which we know that it has achieved great success in calculating the scatter amplitude in the info supermember theory. So in supermember theory, it has been calculated. You know that for 6 points, we calculate up to 8 loops, and 7 points up to 4 loops. Of course, these rather higher loops results are not calculated from the integrand, which is hopeless. What we really do is, although we cannot calculate something from the integrand, but since the theory enjoys a lot of good physical and mathematical properties and structures, so before the integration, you really have some control of the final result, like what kind of transcendental functions it should be, or some physical property, like maybe what kind of physical singularity this function might have. So finally, this information will allow you to write down all the possible functions that satisfy your prediction. So basically, it will form a very big function space that's very reasonable for your observable. And what you need to do is impose the physical condition that your observable satisfy to, say, fix the coefficient between these bases, or say you get rid of the useless candidate. And finally, what you get will be the final result. Okay. So at first glance, you will see that this is really reasonable for our case. What I'll talk about is the 6.2 loop observables today, because we all know that all these observables should be able to expand it by this mass integral. So the 945 functions will serve as a very natural linear basis in our ansatz to do the bootstrap at the beginning point. But as I said, this information is not enough for you to really do the bootstraps, because we have very non-trivial kinematic prefactor for the QCD amplitude, and this kind of QCD prefactors is also one kind of input you have to consider. And finally, write down this kind of ansatz, and here the Cij are the rational coefficient you need to fix. Okay, so it's right into my second concern is we have to get more understanding about what kind of kinematic prefactor a QCD amplitude can have. Okay, so this is all for the motivation. Now let's go to the main object I want to talk about, which is called the Wilson loop with Lagrangian insertion. Gongshu also mentioned this. It's very good for me. Basically, it's definitions like this. This is some formal observables we define in the supersymmetric Yang-Mills theory. And the basic definition is to just take a ratio of these two expectation value. It is from some polygonal Wilson loop, but in the numerator, you insert one more operator from Lagrangian in that. Okay? And diagonally, you can see that it's some ratio like this. Okay? And these observables, because defining an info supermember theory. So firstly, it has a lot of good say mathematical and physical properties. So firstly, the dual conformal invariant. Secondly, because of the very remarkable property called the Wilson loop amplitude duality in the theory, so you can very easily show that in this at the integrand level up to the predictive expansion, this integrand level is corresponding to the logarithm of the original integrand for the scatter amplitude. So it's closely related to the scatter amplitude we're caring about. And the third point, maybe more important for our discussion, is these observables, because the Wilson loop in theory only have divergence from this cusp, or say you exchange some particles near the vertices. So when you take this ratio, you can very easily prove that after the perturbative expansion, all this divergence will be cancelled, and in each order you get only IR and the finite thing. Okay? And so it's very like the QCD hard functions we define after the subtracting of the divergence. But of course, it also has its own simplicity. Because it's very similar to all the other like scalar amplitude in the info supermember theory, because there are some uniform weight functions. You know that the QC amplitude is not the case. Usually they will have rational terms and mixed weight part. So you will ask me why this observable you are expecting that it will give you some insight about QCD amplitude, which is super complicated. Well, this is 2 points that I think is very important for this. The first point is, although this observable is defined in this supersymmetric Yang-Mills theory, but after integrated it to the transcendental functions, these functions will as much complicated as all the Feynman integrals we calculated from the Count differential we just showed. Okay, so we can see these points from the say kinematic input of these observables, and see that firstly it depends on this vertices of this polygonal Wilson loop x1 to xn the position, which in fact after the duality correspond to the momenta of the external massless particle p1 to pn. But beside that, it also depends on the x0, which is the position of the Lagrangian operator insertion. So by the conformal transformation, or say the gauge fixing of this x0 to be the infinity point of the kinematics point, then you can very easily show that this kinematics input, in fact, is exactly the same as that for the n-parton scalar amplitude, or you see that it will depend on 3n minus 11 ratios of these Mendelssohn variables. So in other words, for example, if today I will look into the 6.2 loop observable, and its result can be expanded by the 945 function I talked about. Okay. And another point is very important for maybe a little bit miracle is in all the non-trivial results we obtained for this observable, I think it's up to 4 loops observable up to 3 loops and 5-point observable up to 2 loops. And in this case, we found that the L loop observable in this case, in fact, is dual to the maximal transcendental weight part of an L+1 loop, all plus pure Yang-Mills amplitude. So we can see that we really calculate some part in the QCD part of scalar amplitude. So this is very well, it looks natural because in N-for theory, the scalar amplitude also account for the maximal transcendental weight part of the QCD amplitude. Okay, so of course I want to calculate these observables today, but I will not do a very honest IPP reduction. What I really do will be the bootstrap. But as I said, for this kind of thing, beside the function space you can get from the CD calculation, there's one more information you have to fit with it, which is the non-trivial prefactors. Okay, so for these observables, we have to discuss how to classify its prefactors, such that finally we can write on the ansatz. The basic idea is that is following from what we call the positive geometric pictures under this observables. Maybe some of you are very familiar with this fact that in this N-for theory, it's tree-level amplitudes and the loop level integrand can be calculated from what we call the canonical functions of the amplitude hedron. Okay, so maybe it's a little bit abstract for people not familiar with that. You can imagine that you have some curvy region or some curvy geometries in your kinematic space together with the loop momentum space. And what you really do to calculate the integrand for this amplitude is just to calculate the volume of this geometry. Okay, so it's very strong geometrical and mathematical underlying structures under this theory. For our case, we have said that its integrand level correspond to the logarithmic of the scalar amplitude. So you could expect that there's also some similar geometrical interpretation for this observable. So this is what we call negative geometry expansion. Okay, so I do not have enough time to talk about details. Please see your staff talk on Friday for more detailed review. What you need to need the information for today's talk is, instead of only one geometries whose value correspond to the integrand, today we have our observable correspond to sum over several geometries, and you calculate each of their volume, add them together, you get the volume of the integrand of this observable. And this is something we usually draw like some diagrams, what we call ladders, triangles. And this thing, in fact, generally, they are non-planar. So they're very non-trivial. They cannot be calculated by the Feynman integrals, but there are some underlying mathematical structure for our observable. So what does this kind of thing help us to do the calculation? Well, it can help you classify all the prefactors. Okay, so this looks very miracle, and this is some great work done by Taro Brown and my collaborator Johannes Hahn, Ilya Mazzucchelli, and also Yaroslav Trinka. The basic idea is the following. So all the prefactor in this case, because you are dealing with some maximal transcendental weight function, so all these prefactor can be calculated by the maximal residue of the integrand, what we call the leading singularities. And these leading singularities, or because they are residual, so they are associated with some solution from the loop momenta, and the solution of the loop momenta, which we call the maximal cut solution, are fully controlled by the boundary structure of this geometry. Maybe it's very abstract, but you can imagine that you have some polytope, okay? and you are counting how many vertices, how many facets, how many edges this polytope really has. And finally, this kind of mathematical and combinatorial information will help you to classify all the physical prefactors in this object. Okay? And here I show you their diagrams, which this kind of intersection line, in fact, correspond to the what we call maximal cut solution in these observables. And finally, you can calculate the residue on this solution and get all the prefactor. Okay? Yeah, so finally, their conclusion is up to any loop and any point. So this is really, really strong. I hope I didn't make any mistake. This linear similarity for these observables can be expressed by the linear combination of these Kermit functions, which are some rational functions, and was already seen 50 years ago for the one loop MHP amplitude integrand. But it's also very interesting because we said that their conjecture, there is some duality between our observable with all plus Yang-Mills amplitudes. So you imagine that if you have the gauge fixing, they also serve as the basis for the QCD prefactors. Okay, so let me have a quick recap. Now we have the mass integrals from the canonical differential equation and the prefactors, kinematics prefactors from the geometric input. So now it's our time to fix all this number coefficient and get the observables. So more details for this ansatz, you have 945 functions from the canonical differential equation, and in fact, you can count in the number of the independent linear combination of these Kermit functions, and you get 20 in this 6.2 loop. So generally, your ansatz look like this, but this kind of thing, this kind of coefficient, you have naively 20 times 945. But of course, this observable is some dihedral invariant thing. So finally, begin with the dihedral ansatz, you have 17 and 18, these many unknown coefficients. Okay, and then you impose all the physical conditions this observable satisfy. Usually, if you look into any bootstrap paper, there will be a lot of table like this. And here we list all the physical conditions that we consider that this observable satisfied. You can see some of them is very really just from some physical principle like soft and collinear, means that after you're taking the things, go back to some lower point observables, which are known. And also have some spurs, something equal to 0. This means that because of some of the linear similarity, they have some spurs posed when you're taking the residue, they have non-trivial residue, but the whole observable will have 0 residue on that, so it also gives some constraints. And for all these conditions, we list the numbers of their constraints from each of the conditions like this. So for our case, it's weight 4, and we have these constraints here. Okay. So the conclusion is, if you impose all these physical conditions at the same time, you can fix all the coefficients and finally get this observable. And then one thing I think is very interesting in this calculation is, you can see that the collinear and soft condition is really strong in this case. This is, and if you impose that, in fact, kills 90% of the coefficient. This is very reasonable because the hecton space, and after taking limit, you go to the pentagon space. These two function space are both very non-trivial. But here's really some simplicity. You can do a comparison. You can do a 5-point bootstrap, begin with pentagon functions and 5-point linear similarity, which is smaller ansatz, but you impose the same physical condition, you'll see that you cannot fix this observable. Okay, so it's just because you have more complicated off-value and more complicated functions, you have this simplicity. In fact, this is not the first case we observed that. 10 years ago, by this paper, a symbol of uniqueness, we already see that for 7-point observables, 7-point scalar amplitudes, it is easier to fix than the 6-point amplitude in the super Yang-Mills theory. Let me give you some taste about this bootstrap result, because a result of super big, I cannot show that. Yeah, I think Anastasia this morning also mentioned this 245 two-loop planar letters. Among them, only 137 really in our observable. Half of them are ruled out. And among these, in fact, only 48 letters really some two-loop letter, means that you will first encounter them when you really go to some two-loop sector and calculate your canonical differential equation. And they can be contributed by these 5 non-trivial from integral sectors. And I think Anastasia mentioned that there's 24 letters are missed. In fact, they are contributed by these 2 from integral sectors. Okay? And for example, some of the sector will be ruled out, and these letters are totally absent in this result. But this is really interesting question, because we know that most cases, I think Ruth yesterday also mentioned that most cases, if you express an amplitude into a set of Feynman integrals, then the Feynman integrals is in principle more complicated than the scalar amplitude, because they may introduce some spurious singularity or spurious letters, which may cancel out in the final result. However, in the other hand, if a letter or singularity really appear in observable, then it has its reason to be there. There should be some principle to help you to find this why it should be appears in some sense. So this is some question we want to ask, why only these 5 diagrams really contribute. And in fact, we borrow some idea from Brown's group, these people 7 years ago. The basic ideas from the boundary structure of the amplitude will also take control of the singularity for the final integrated result. Okay, so I do not have enough time to go into these details, basically because we also have some geometrical expansion, and this geometrical expansion is a boundary structure. We say that it can help you to classify all the prefactor, but in fact, they can also help you to classify all the singularity that will happen, that will appear, or say the symbol letter will appears in the final result. So these diagrams will helpful again, and you write down which we call the Landau diagrams, do the symbology or say Landau analysis for this, and finally you can get this 137 letter very straightforward. Okay. Oh, sorry. Yeah, please, if you're interested in the details, please refer to Ilya's poster, and he and I will be very happy to explain more detail about this. It's the work done by with Dmitry Checherin, Johannes Han, Ilya Matsukiri, Yaroslav Trinka, and Shen Qingzhang. Okay, so finally is the miracle part. We said that there's a duality between our observables with all plus Yang-Mills amplitude. So it's still a conjecture. We only observed this duality really works by now is for the 4.3 loops Yang-Mills amplitude and the 5.2 loops Yang-Mills amplitude. Yeah, so here I give you the duality explicitly. You can see that take product of our observable with hard functions of the MHV amplitude in the super Yang-Mills theory, it will correspond to the maximal transcendental weight part of the hard function for the pure Yang-Mills amplitude. And you expand it by the coupling constant, you see that this order is really the thing we're talking about, is dual to the QC amplitudes. Okay? So it is conjecture that this combination will correspond to the maximal transcendental weight part of the 3-loop all plus pure Yang-Mills amplitude. So here's, this is of course a conjecture, but here's very strong evidence for this. You can look into our bootstrap result and check the Steinman relation, and see that this result is not satisfy the Steinman relation. It's very reasonable because I said that in integrand level, it's logarithmic of the original scalar amplitude. So its integrand will involve some product of 1 loop amplitude, which will defy the Steinman relation. However, if you add these 2 terms and to check the Steinman relation of the whole combination, you will see that the Steinman relation will satisfy again. So I see that it is very strong evidence that really still hold for this result, and we expect in the future we can really check this duality to be true. Okay, so finally, let me give some summary. Yep, so the most important point in this study is we get some the first time we get some amplitude-like observables in this novel 2-loop planar hexagon function space. So it really gives us some feeling about what the QCD amplitude bootstrap should like and what kind of feature this amplitude can have. And the 2 main complexity in calculating the QC amplitudes in our case are solved by the following. So firstly, instead of IPP reduction, because we have the function space, so we do the symbol bootstrap. Of course, this procedure can be applied to any observables that localize in this function space, because they can always be expanded by the master integrals. And there's really a simplicity I want to emphasize, because 6-point bootstrap is simpler than the 5-point bootstrap. So you could expect that if you can write on MDOT for the target observable, it's very possible you can fix that. Okay. And second point is, all the linearity for the QC amplitude is a very complicated task, but for our case, we have a very elegant geometrical framework which helps us to classify this linearity and write on MDOT. Of course, if you go to the more physical, more other physical channels of the QC amplitude, it still remain very huge challenges. But here may be some insight for you. Some paper by Johannes and William about 3 years ago, I think. In fact, there is a claim in the paper that if you look into the maximal transcendental weight part of this QC amplitude, its prefactor should also enjoy very similar properties as the singularity linear singularity we talked about today. So you can imagine that in the future, we can also get for the prefactor for the lower weight, we will also want to try if we can get an understanding for that. And finally, I think some of the direction is very interesting. In all today's talk, I only talk about the symbol level. This is because all the mass integrals from the canonical differential equation are not integrated for the function level. So it's very interesting. After we get the function level result, we can do a function bootstrap. It can help us to check some of the good function property like positivity and complete monotonicity property, which is very important also for us to understand this function from another aspect, and also do like some numerical bootstrap. Yeah, I think this is all I want to say. Thank you.